Hello everyone, welcome again to this second session of today's CosmoverseLectures Lectures at Your Desk. Our speaker now would be Gagandeep Anand. Dr. Anand is a senior staff scientist at the Space Telescope Science Institute, working on the advanced camera for surveys, one of the two operational imagers of the Hubble Space Telescope, and he's also a member of the SCHUSS collaboration. Dr. Anand is also an active member of Cosmic Flows and FANGs, two other cosmological collaborations, and his main research area is near-field cosmology with resolved star populations, with a particular focus on extragalactic distance scale. Today's lecture is named Tip of the Red Giant Branch Stars as distance indicators, and he will be telling us about it more now. So please, the stage is yours. Start whenever you want.
Yeah, thank you. So thank you to the organizers for inviting me to give this talk. Thank you for all tuning in, and thank you to Luis for the great lecture on Cepheids. And so I'll be talking about tip of the red giant branch stars as distance indicators, which in many senses are very complementary to Cepheids. And so I'll briefly go over the history and methodology behind the tip of the red giant branch, or the TRGB. I'll speak about it in the context of the Hubble tension, as well as in the area of JWST and beyond. And so the underlying principle behind the tip of the red giant branch is that as low mass stars like our sun, once they go off the main sequence, they will track all the way up the red giant branch. And so as they're tracking up the red giant branch, what they're doing is they're fusing hydrogen together in a shell around an inert helium core. And they continue doing this up until they reach the point that we call the TRGB. And at this point, they undergo the helium flash, which marks the onset of helium burning within the star. And the key point here is that the physics that dictates this means that the maximum core mass at the TRGB is essentially a constant. And so we can use the stars at the TRGB as standard candles with a modest metallicity dependence depending on what wavelength you're looking at. And so the method began to really gain steam, I would say, in the 1990s with some seminal papers and benefiting from key imaging technologies and better observing facilities. And so the I band, or around 800 nanometers, provides a very stable wavelength regime to measure the tip of the red giant branch because of the limited metallicity and age dependences. And so on the right here, you see a plot from Lee et al. 1993. This is one of the seminal papers. And on the top panel, you see the isochrones that show the predicted behavior of the TRGB in the I band magnitude as a function of metallicity. And you can see that dashed line is very stable, or it tracks those isochrones very well. Whereas in something like the V band around 600 nanometers, the feature is a sharp function of metallicity. And in the bottom, again, you see the I band, and now we're just showing the variation with age, which again is very small. And so skipping a little bit of history and going to the present day, we have distances to something like 500 galaxies that have been determined with the tip of the red giant branch using the Hubble Space Telescope as part of the extragalactic distance database. And so this is work that is done by members of the EDD collaboration, taking all the imaging that's available with Hubble and sort of uniformly processing it to measure these distances. And one of those galaxies is shown here in the top right. Most of these distances with Hubble have been determined within 20 megaparsecs, but there's some extension out to 20 to 25 megaparsecs. The reason why it's limited to about 10 megaparsecs is, and I'll talk more about it later, but that is the distance you can reach with the TRGB within one orbit, or about 90 hours of wall time with Hubble. That's the sort of minimal unit of currency that you can observe with Hubble. And so these distances, of course, serve as the basis for a broad range of science, not just focused solely on the extragalactic distance scale, For one, distances are important if you want to study galaxies or their stars because they allow for the determination of accurate physical parameters. You don't know how big a galaxy is or how bright its stars are until you know its distance. Additionally, these distances allow for the mapping of local large-scale structure, and they serve as a key foundation for the Cosmic Flows program. And so doing things like mapping our home supercluster Laniakea, shown here on the right, these are all made possible because of the foundational work that the TRGB allows. And of course, the focus of this talk, given the audience and the venue, is setting the extragalactic distance scale and performing measurements of the Hubble constant. And so that's what I'm mostly going to focus on from now. And so here what I'm showing is a mock or a synthetic plot of what different stellar sequences would look like in typical Hubble Space Telescope filters. On the y-axis, you have the I-band magnitude, and on the v-axis, you have the color, V minus I, so that bluer stars are to the left and redder stars are to the right. And so you see different sequences labeled going from left to right. These are main sequence stars. You have your helium-burning stars, your blue and red supergiants. And then on the right, you have the giant branch, which the lower part is the red giant branch, which terminates at the tip of the red giant branch. And then above that, you have thermally pulsing HEB stars. And so translating that sort of synthetic diagram, here's an actual color magnitude diagram from the Hubble Space Telescope. This is for this galaxy here, this dwarf galaxy at about 3 megaparsecs from the Milky Way. You can see the stars are beautifully resolved individually, and that's what we use to make the tip of the red giant branch measurement. So you can see the blue main sequence stars at about a X value or a color of 0, but then you can see that the prominent feature on this color magnitude diagram is indeed the red giant branch, and the tip of the red giant branch is labeled with the sort of broken solid line there. And so, as I've said before, the distances are vital to understanding the physical properties of galaxies and their stars. And so, even if you don't care about cosmology, you need to have good distances if you want to study these objects. And the TRGB has been proven a really highly efficient way to measure these distances. The reason the TRGB has been used so much is because you don't need as much time typically, because you don't need to generate a light curve. Largely, these stars are not variable. They are at the sort of very millimag level. And so that means they're more efficient. And so with Hubble, you can go out to about 10 megaparsecs with one orbit, or about 45, 50 minutes of actual observation time with Hubble. With JWST, which I'll talk more about later, we're finding that within about 2 hours, you can actually go twice the distance with 20 megaparsecs, and we think we can push it to 50 megaparsecs with sufficient investment in an individual observation. But even the 20 megaparsec threshold, that's almost an order of magnitude increase over what Hubble was routinely able to do. And in many senses, it's complementary Cepheids, but it's also usable in situations where you can't use Cepheids. So, elliptical galaxies, for instance, or dwarf spheroidals are not going to have enough Cepheid variables or any Cepheid variables. And so you wouldn't be able to measure the distance that way. The TRGB, you can use it in all manners of galaxies, provided that those galaxies are sufficiently massive enough to have a fully populated red giant branch that reaches the tip. And that is a valid premise up until, quite faint into the dwarf regime. And so in terms of actually measuring the tip in practice, there are two main techniques that are used in the literature. The first is families of edge detection routines, such as the Sobel filter. And these effectively are measuring the derivatives of the underlying stellar luminosity function that break in that you see that I showed you in the color magnitude diagram. The second are model fitting routines that typically fit a broken power law model to the same underlying stellar luminosity function, where the break denotes the location of the TRGB. And so edge detection techniques are common in the literature. The premise is that you first, at a very small level, bin, and then optionally smooth your underlying stellar luminosity function, and then you run this edge detector along the luminosity function to measure your tip of the red giant branch. So that's what's shown here on the plot in the right from Jang et al. 2018. This is the same luminosity function for NGC 1365. And it's, 1, 2, 3, 4, 5, 6, 7, 8 different ways of doing the Sobel technique, but they all largely agree to the uncertainties. That red line, the blue histograms are showing you the underlying stellar luminosity function of the giant branch, and the red lines are showing you the edge detection results, and the peak of that corresponds to the TRGB feature. You have to be careful sometimes, particularly with low signal to noise data. The presence of multiple peaks can happen, and that confuse the matter. There are some benefits to doing things like weighing the edge detection outputs, so further modifying them, but they may generate small biases. And the other class of measuring the tip is these model fitting techniques. They typically fit a broken power law model to the giant branch luminosity function. So on the plot in the right, you see this color magnitude diagram for this dwarf galaxy DD070. And on the bottom right, you see the luminosity function and the fit to the luminosity function. And so this is typically a 4-parameter model. One parameter is the slope of the AGB. The other parameter is the slope of the RGB. And then you can see at about 21.79 magnitudes, that's where the TRGB was found to be. And so the other two parameters are, of course, the location of the TRGB is what you're solving for, but also the strength of the TRGB discontinuity. And you can see that by seeing that there are, in this galaxy and pretty much all galaxies, there are many more RGB stars than there are AGB stars. And so that dictates your strength of your TRGB discontinuity. A nice benefit of this method is that it allows for the straightforward inclusion of artificial star results. And so things like photometric bias, errors, and incompleteness. This is especially useful when you're looking at the really low signal to noise data. So in the top right of the plot, you have the very top panel shows the completeness as a function of magnitude. And it's basically, close to 100% complete at the TRGB. So it's not a huge issue in this case. But then in the bottom, you see the photometric errors. And then as the errors tick up, the bias also ticks up. And so in cases, again, where you're dealing with low signal to noise data, it's good to model all of these observed quirks. Typically, you see good agreement between the two techniques, so it's fine to use either. There have been studies that have shown with various samples that they agree generally well. But again, they may disagree in the low signal to noise regime, where it just becomes harder to measure the tip. A good rule of thumb is that you want at least 1 magnitudes of observations below the TRGB, such that at your tip you have a sufficient signal to noise. If you want a really precise measurement, below better than 5%, it's better to be 1.5 to 2 magnitudes above the TRGB. And so, in the context of the Hubble tension, Luis did a good job summarizing the Hubble tension, but I'll give it the little TRGB spin here. And so, there's this plot on the right I'm showing, and all I've done is I've gone into ADS. The abstract search system and did a title search for the words Hubble constant. And you can see there's this sort of behavior in the numbers of papers published every year. And so before the results of the Hubble Key project led by Wendy Friedman, there was a lot of work going on to figure out what the value of the Hubble constant was. With those seminal results, we were pretty settled on a value of the Hubble constant of about 72 plus or minus 8 kilometers per second per megaparsec. But of course, that's, the story began to turn. Work by the Shoes team, among many others, as I'll get to in a second, find a value using a Cepheid and Type 1a supernova distance ladder of about 73 kilometers per second per megaparsec. And with the latest iterations of Shoes results, this is pushed below a 1 kilometer per second per megaparsec uncertainty, almost into the 1% regime. But on the other hand, the results that are derived from the cosmic microwave background, extrapolated to the present day, they give a value that's a fair bit lower, especially when you take into account the small size of the error bars. And so we're left with this Hubble tension that is approached over 5 sigma at the present day. And I want to be clear, this is not a shoes versus Planck issue or a shoes versus CMB issue. It's worked by many different groups on both the early universe side, which is the sort of left-hand green bar you're seeing in the plot, versus the direct sort of measurements of the Hubble constant. I'll call them at the present day using things like standard candles, which are scatter about the red area in that plot. And that's that Hubble tension you're seeing. And so, you know, if the Planck and lambda CDM's prediction of the Hubble constant at the present day is correct, then shouldn't the local distance ladder method scatter about the Planck value? Well, we see that they clearly don't. And so, you know, this begs the question, what is wrong with all of our distance indicators and the way we're doing these experiments? Or more tantalizingly, is there an issue that we've uncovered with lambda CDM? And that's a very intriguing question, but we ought to be sure that, you know, we've done something, you know, that we haven't messed up in the local distance ladder. And so, you know, I mentioned the shoes results, but a lot of this work has been pushed forward by the Carnegie Chicago Hubble program. And what they did is sort of replacing Cepheids in the distance scale and using these tip of the red giant branch stars that I've been talking about. And so they're using the TRGB to calibrate the type 1a supernovae in nearby hosts. And so here you see a panel from one of their main papers. Those hatched regions show where in these galaxies that they've observed the TRGB stars. And so you'll, you know, you can compare this to Luis's talk, but the regions that you're measuring these stars are actually very different. Red giant branch stars also exist, you know, in the disks of the galaxies, but it's best to measure them out in the uncrowded halo where you're less affected by things like crowding and dust. And you also find lower metallicity RGB stars, which are more stable for measuring the tip. And the first major result from that team, and there have been subsequent results since then that effectively show the same thing, is a tantalizing result that's in the middle of the CMB and the Cepheids, and so it's perhaps easing the tension, but I'll talk more about that later. But this is sort of the setup. You know, members of the extragalactic distance database team, we performed an independent reduction of the full CCHP HST data set, and those are you can see those two panels on the right, those two measurements on the right. So the blue, looking at the blue ones, are the late universe results. The first one is the shoes result from Cepheids and supernova, but then the next two are replacing the Cepheids with the TRGB stars. And you see they come in a little lower. And so perhaps there's something interesting going on there. Perhaps it's easing the tension. But I'll talk more about that in a little bit. And so what are we seeing now with JWST, which has been up and flying for a few years? And I'll talk a little bit about what comes after. And so early imaging from JWST, here is an example color magnitude diagram. I think maybe the first one, actually. This is for a nearby galaxy very close by, 1 megaparsec. It's a dwarf galaxy, WLM, and it is incredibly deep. You know, this thing is going down to 31st magnitude in the I band almost. You know, if you put this galaxy further away, you could measure its TRGB distance probably out to 50 megaparsecs with these observations. And so that's an incredible increase in volume over Hubble's capabilities, where 10 megaparsecs was routine, and you could go 20, maybe a little bit past 20, but with very substantial integrations. And so this is immediately a big jump in observing capabilities. But there's a caveat at the moment, and actually part of it has to do with how powerful JWST is and how sensitive JWST is. And that is that direct calibrations of the TRGB, that is actually calibrating the absolute magnitude of the TRGB directly in the JWST filter system, are limited to this single anchor galaxy, NGC 4258, that I'm showing here on the right. And so there, with HST, we were able to perform other calibrations, and also using ground-based facilities, but directly in the JWST system, this is the only anchor that is at the right distance to do these measurements. There are ideas about how to use JWST to extend it to the LMC and the SMC and perhaps other facilities, which I'll talk more about, or other galaxies, which I'll talk more about. But for now, this is a key point to remember, that this galaxy is very important to the JWST TRGB distance scale. And so I'm going to have to do a little bit of an aside, but the preamble for that is that some programs with JWST, for example, the SHOES team, have gone to effectively measure what is the I-band TRGB. So that is the sort of transition between optical and near infrared. To others, like the Carnegie Chicago Hubble program, have chose to go with a near infrared filter, F115. Which is a little redder in color. And so my aside for now is, okay, what's going on with the near infrared TRGB? And so why would you want to go there in the first place? And the easy answer is it's brighter. So it's a brighter feature. You get more signal to noise on the same time. But unlike the I-band TRGB, the near infrared TRGB is a strong function of color, which is a proxy for metallicity and age in the near infrared. And so you can see this plot here on the right in Durbin et al. 2020. There's a very steep relation between color and magnitude in the near infrared TRGB, and this was shown in the pre-JWST era by many authors, some of them shown here. And so you have to calibrate this. It's another step in the calibration for the near infrared TRGB. But of course, this is doable. And so, I'm showing one example here, but many of those papers I listed on the earlier slides also show good examples. You can actually, you can rectify the slope. So that is, you measure the slope in your tilted color magnitude diagram, and then you actually flatten the slope out, and you can basically do your TRGB measurement as if it was flat in the first place, like the I-band. And so what does that look like? Well, there's good agreement in the near infrared HST filters. This is from that same paper by Newman et al. You can see the calibrations overlap pretty well. With JWST in the I-band, actually we've already achieved really good agreement in the I-band filter system in JWST. Work by 3 different groups with 2 different sets of observations, all agree to 1%, amazingly already. But what about the near infrared TRGB with JWST? And so there have been some papers that provide the first empirical calibrations in the near infrared for JWST filters. And so again, you're doing 2 things now. You have to measure the slope as well as the 0 points. So there's fair agreement between I say 2 studies here. It's the Newman paper and then the Hoyt 25 paper. There's a fair agreement in the slopes. They agree within the uncertainties, but the 0 points at the same color right now differ by about 1/10 of a magnitude, or 5% in distance. And so if you want to do things like measure 2 to 3% precise distances, this is not going to work at the moment. And so we need to sort this issue out before we can use the near infrared TRGB to the same stability that we can the I-band TRGB. Additionally, not just with the 0 point, but also with the slope, we're seeing that there's some issues with the behavior of the slope. Here's an example in the 0 point calibrating galaxy that I told you was really important. This is NGC 4258, and this is very nearby. This is closer than almost all but one of the supernova hosts. There are 3 different fields that show a factor of 5 spread in the slopes between 0.2 and 1. And so this raises concern about the usability of the near infrared TRGB as a standard candle. And so I think at the moment, best practices are folks are still working on how to try to determine what the best mechanism is for the near infrared TRGB and how to use it. And again, I want to reiterate, there is a reason to use it, in that it is brighter. The TRGB is brighter in the near infrared wavelengths. You can, in the same amount of observer time, you can get further. And so this plot on the right here from McQuinn et al. 2019 shows synthetic photometry in a number HST, JWST, and ground-based filter systems, and the difference between the FO90 filter, which is the 4th one there, versus the F115 filter, which is being used by some groups, is about 0.6, 0.7 magnitude. So it represents a a decent increase in capabilities, but again, we need to figure out what's going on with the calibration first. And it's unclear to me at the moment what the ultimate precision of the near-infrared TRGB will be. So another reason why folks are using the near-infrared TRGB is actually with the cameras on JWST, with the main camera, you can actually get 2 filters simultaneously, and that allows you to have more efficient observations if you're doing only near-infrared, if you're doing the near-infrared TRGB. But there's a caveat to that also, in that the long wavelength channel, which is what you're using for the color measurements of these stars, actually has a noticeably worse resolution. You have 4 times the amount of area of sky within the same pixel, and so this could be particularly troublesome at larger distances. And so here's an example from an observing program. This is at 19 megaparsecs. This is I close to the far end of what we've observed so far with the TRGB and JWST. And so on the top, you see the quality of the short wavelength imaging. So if you're using the optical TRGB, the I-band TRGB, and that same image shown in the long wavelengths channel, which you need for the near infrared TRGB, the image quality immediately degrades even in the galaxy halo. Crowding will become a problem, particularly if you want to push this to further distances. And so I think this is something we need to be careful about. And so, okay, near infrared TRGB aside is done. Let's go back to what's going on with JWST. And so, as I've mentioned, different groups have picked different observing strategies. Putting that aside for now, here's an image of one of these supernova hosts. So this is one of the further ones, NGC 3370, and you can see the color image, but you can also see the inset. And so outside of that inset region is where these TRGB measurements are done. And in that region, there's very low crowding, but the stars are still well resolved. And it happens to be the case that between 3 observing programs from cycle 1 and cycle 2, between the SHUS and the CCHP teams, folks have already imaged the hosts of 19 supernova 1A with JWST. You can compare this to 42 supernovae that are used in the Cepheid distance scale, and we're already halfway there. There's some more cycle 2 data from another project, which adds 3 more, so it's actually 22 with JWST. And so what have we learned from this sample? As I mentioned earlier, there was perhaps signs of the TRGB sort of easing the tension between the CMB and the Cepheid results. And so now with a bigger sample, what can we say? And so generally speaking, I think the first point is that at the moment, distance is measured by different groups, whether it's the Carnegie team, whether it's the SHUS team, whether this is the Cosmic Flow / Extragalactic Distance Database team. They agree very well, and so that's a good place to be. The TRGB distances, when you compare them between individual galaxies, so you're comparing the distance to the same galaxy, they agree on average to within about 1%. And so what I'm showing here on the right is a comparison of the Hubble Space Telescope Cepheid distances versus all other methods, HST or JWST. And so this is showing Hubble Space Telescope Cepheids versus JWST Cepheids. It's showing it versus JWST and HST TRGB, as well as a couple other distance indicators, JAGB and MIRAS. And so if you look at that inset, what that's showing you is the difference in magnitudes between the HST Cepheids and all these other systems. And you can see that with the TRGB, it agrees to well within the uncertainty, and it's only about a percent difference, whereas the Hubble tension is something like 8 or 9%. So this is the TRGB. When you compare it from galaxy to galaxy, it's not going to alleviate the Hubble tension. The reason it was appearing to alleviate the Hubble tension is actually just sample selection earlier. And so when you do this big test of the Cepheid distances measured with Hubble and you compare them against TRGB, JGB, MIRAS, they show very good linearity in their distance scale. And what that's telling us is that the Cepheid distances are really good close by, but they're also really good at the far end of where we're measuring the distances. They're very linear, and there's no clear signs of remaining issues with the crowding issue that, for instance, that Louise spoke about in her talk with Cepheids. And so I think this is a really key result in that for now, the distances agree really well. And okay, I mean, that's pretty much it. The Hubble tension is real. It's up to the theorists to solve it, right? I don't think everyone is convinced at the moment. I get kind of a 50-50 split from the community is my sense, which is 50% is like, okay, it's real. The other 50% is like, I still don't believe you guys. Okay, we'll try to make you believe us. And so, here's the Shoes distance ladder. It's the 3-rung distance ladder where you first calibrate the brightness of Cepheids with geometry. Then you use those Cepheids to calibrate the brightness of type 1a supernovae. And then you use those type 1a supernovae in the Hubble flow to measure your Hubble constant. And so the Shoes distance scale in that second rung has 37 host galaxies, some of them multiple supernovae. So there's 42 type 1a supernovae that are being calibrated. And we, as I've shown, we can replace the Cepheids with the TRGB, and it doesn't really change the story. The distances agree really well. But those supernovae, right? What about what's going on at that end of the distance ladder? And so there are remaining concerns about type 1a supernovae. What is the nature of dust in other galaxies compared to the Milky Way? The fact that the Cepheid calibration by its nature is limited to late type or star-forming galaxies only, et cetera, et cetera. These are issues that people know about, and for the dust issue, people are working on. But they're open questions. And of course, what about unknown unknowns? We don't understand the progenitor mechanism behind type 1a supernovae. What they teach you to undergrad isn't really what's going on. We don't actually know things that well. And so what we need is a distance ladder that does not rely on Cepheids, that does not rely on type 1a supernovae. We need an independent ladder. And so TRGB can take the place of Cepheids, as we've shown, but what about type 1a supernovae? And so I'll briefly foray into what are known as surface brightness fluctuations. And so the idea behind surface brightness fluctuations these are not individual events like type 1a supernovae. It's the premise is that the number of stars per pixel varies with galaxy distance, and so more distant galaxies will have a smoother profile. And you can see that in this in these images down below, where you see 3 different early type or old stellar populations at different distances, and as you put them out further out, their profile becomes smoother. There's less modeling just because of the target's distance. And these rely largely on the same RGB stars as the TRGB does, and it's a good match in that sense. And what about, okay, how well can this method do compared to supernovae? Well, one, there's no shortage of targets, right? With supernovae, you have to wait for the things to blow up. But with type 1a, so with surface brightness fluctuations, elliptical galaxies just exist in the universe, so you can use them. And there's no need to measure the light curves. There's only a single epoch of data needed, and the precision per target is very competitive relative to the supernovae. And indeed, this has been done before to some extent. And so the infrared surface brightness fluctuations were used to measure the Hubble constant in this paper by Blakesley 2021. And they found a value of 73.3 plus or minus 0.7 plus or minus 2.4 kilometers per second per megaparsec. The plot on the right shows a very different, slightly different value, and that's just due to how you deal with the velocity uncertainty, which I'll talk about in a second. And so this feeds into some of the limitations of this HST surface brightness fluctuation work. There's 2 main limitations that I see. One is that there were a limited number of calibrator galaxies. How do you actually calibrate the brightness of surface brightness fluctuations, the fiducial brightness? It was previously the case that it was a mix of 6 Cepheid and 2 TRGB calibrator galaxies. One problem is they're already mixing 2 different types of calibrators there, which is not optimal. And 2 is that you only have 8 calibrators. The other is that the peculiar velocities that we're measuring with Hubble at SBF distances are not small. These are galaxies that are mostly between 50 to 100 megaparsecs. And so their velocities are, while still largely dominated by the expansion of the universe, by the Hubble flow, the peculiar velocities that are result as a function of galaxy-galaxy interaction. So, galaxies in clusters or galaxies in the field interacting with other galaxies, those are non-negligible. So you have to correct them out. And so these are, depending on what model you use, it gives us slight differences, but it would be great to sort of bypass both of these limitations, both with the calibrators and both with the peculiar velocities. And these can be both dealt with by using JWST. And so out of the need for an entirely new, what I call what we're calling a population 2 distance ladder based entirely on old stars, the TRGB SBF project was born. I like to point to this email by my PhD advisor who sort of kicked things off with this email. I would like to propose a 2-step program. It turns out it takes a little bit more than 2 steps, but the idea is to use TRGB and SBF to provide insight into what's going on with the Hubble tension. And you know, here's some of the cast of characters, but we're working with a lot of other collaborators on this as well. And so at the moment, you know, I've said that we can overcome the limitations of the HST surface brightness fluctuation ladder by using JWST. And so that's exactly what we're setting out to do. So we have an approved and actually completed cycle 2 program. And what that does is that establishes the link between TRGB and SBF. That's the second rung of the distance ladder in the JWST filter system with observations of 14 nearby galaxies. We have a cycle 3 program, which is going to calibrate all of the age and metallicity effects for surface brightness fluctuations by looking at galaxies that are at the same distance. They're in the COMA cluster, a rich cluster at 100 megaparsecs. And then we have a couple cycle 4 programs. So we have a cycle 4 program, which is upcoming, that will strengthen the link between the TRGB and SBF. So as I mentioned, the SHOES system for Cepheids and Type 1a supernovae has 37 calibrators between Cepheids and Type 1a supernovae. With this program, we're going to jump the TRGB and SBF up to 25, which is already getting close. And we're also going to strengthen the connection between the Hubble and JWST distance scales. And then, of course, the last thing to do is actually measure the SBF out into the Hubble flow at large distances. And we have an approved survey program, which will collect some random subset of 300 targets to begin generating that JWST SBF Hubble diagram. And I want to talk a little bit about why this is such a neat experiment. And it's actually partially to do with the detector design of JWST. And so the elongated camera you're seeing with the 2 sets of 4 chips, that's NIRCam. That's the main imaging module on JWST in the near infrared, at least. And it's showing that we can get the measurements for TRGB and surface brightness fluctuations at the same time. And what that means is, or what that looks like is right there. And you basically what you do is you put one module in the core of the galaxy where you do your SBF measurements, but then you have your other module out in the halo where you can do your TRGB measurements. And so with the cycle and 2 and 4 programs, we're going to have 25 links between TRGB and SBF with the same camera on JWST. And so here's that SHOES distance ladder that you all have seen a number of times already today. And so the idea with the TRGB SBF project is to replace every single one of these pieces of this ladder. That is, with the initial calibration, which right now we're doing with NGC 4258, but we'll include Gaia as well. We'll calibrate the absolute brightness of the TRGB. In the second rung, we're calibrating surface brightness fluctuations with TRGB. And then in the final rung, we're going to measure surface brightness fluctuations out at large distances, which will allow us to derive the Hubble constant. And a key point here is you can do this all with the same camera on JWST, the near-infrared camera. The SHOES group has worked very hard to do sort of a similar thing, and that is measure the Cepheids in the same photometric system with Hubble. We can do one step better with the TRGB and SBF because we can also do the final rung measurements in the same camera. So versus the SHOES distance ladder couldn't measure supernovae all with Hubble, we could do SBF all with JWST, just like we can do with TRGB. And so here's a footprint of one of those observations on a very low resolution ground-based image that I think hadn't fully loaded in properly now that I look at it. But you can see I've highlighted 2 of the 8 chips in white. And so this is the JWST imaging of the core of the galaxy. And so you can see here, you can see the core really well. You can see globular clusters and a few background galaxies, but you don't resolve the individual stars very well. And that's where you best do your surface brightness fluctuation measurements. You have the sort of modeled nature of the image. But if I go out in the same pointing into the halo of the galaxy, you have what essentially looks like a deep field. This is, a nice, JWST, no matter where you point, you're going to see background galaxies aplenty. But you see all these little dots there, and those are the red giant branch stars that we're using to measure the tip of the red giant branch. And so the first results from this program provide distances to 13 out of the 14 galaxies. One came later, so we're still working on that. For purposes of a TRGB SBF calibration, the color magnitude diagrams are really high fidelity. As you can see here, they're very high signal to noise, very several magnitudes above the faint limit. And the measurements are performed 2 different ways, and there's good agreement. And so JWST is going to be really good for this kind of experiment, is what we're finding. And so taking that a step further, what's going on with the project. So the next step was to actually recalibrate the HST surface brightness fluctuation ladder with JWST TRGB. So I mentioned how there was a mix of Cepheids and TRGB calibrating the HST surface brightness fluctuation ladder. We've removed all of the dependence on Cepheids, and we're only using the JWST TRGB. It turns out it gives you pretty much the same answer, which I guess is maybe not a surprise. But there's more work incoming on also increasing the HST SBF sample from something like 60 galaxies to 200 galaxies. We're also, as I mentioned, performing measurements of JWST surface brightness fluctuations with the same data. Because you have to go much fainter to do the TRGB measurements, the SBF measurements are extraordinarily high signal to noise, several hundreds. And so the power spectra that you measure for the surface brightness fluctuations are very clean. In cycle 3, if this talk was happening a week later, I would have showed you the observations. The observations are actually happening starting in a couple days. But we have 40 fields in the Coma cluster, which is the nearest very rich cluster of galaxies. And we're going to calibrate the SBF metallicity and age effects. This image shows a sample of the Coma cluster and what our fields will look like. The orientations will be different in practice. So it's not going to be exactly like this, but we'll cover all the same main galaxies. And then in cycle 4, we're going to start going out properly, I would say, into the Hubble flow and also strengthen the TRGB SBF connection. So we're looking forward to that. And then, as I've mentioned, NGC 4258 right now is the sole calibrator. That color magnitude diagram is shown on the right there. At present, what we're doing is we're taking advantage of the fact that the TRGB is flat over a small color window. If you actually try to carefully measure out what the non-flatness is there, it does have a very small impact on the distances, about 1%. We're currently in the process of writing that work up. But again, arguably right now we're limited to the single calibrator, but there's ongoing work by multiple groups to try to calibrate the TRGB to the Gaia standard as well. And so, for example, there's a cycle 3 program that will try to do this in nearby dwarf galaxies. Check out that program. And lastly, we're going to need a really well sampled SBF Hubble diagram. The cycle 4 survey program will be a really crucial starting point for that. Okay, now going out a little bit into the future. So Roman Space Telescope, this will launch in somewhere between 1.5 years to 2 years from now. It's got the same size mirror as Hubble, but due to advances in detector technology and design, the field of view of Roman will be huge. And so you can see down there what the field of view of an individual JWST observation or an individual Hubble observation is, and you can compare it to the size of Roman. And so what that allows you to do is actually you can map entire disks and halos of galaxies within just a single to a few pointings. And this is basically not possible with Hubble or JWST because you're not going to get the time to do it. But with Roman, this will allow us to quantify any remaining systematics in the TRGB methods, as well as all the other standard candles. And if you care about things like satellite galaxies, finding satellite galaxies, measuring their distances and luminosity functions, this will allow you to do that really efficiently. So we're really looking forward to Roman in a couple of years. Looking, I'll say 20 years from now, the NASA's next main flagship, the General Purpose Astrophysics flagship, And I would say the true successor to Hubble will be the Habitable Worlds Observatory. And the reason I say true successor to Hubble is because this will be a 6+ meter primary mirror with ultraviolet, optical, and near-infrared imaging and spectroscopy. And the capabilities of HWO, while not fully decided at the moment, will be very, very good for the distance scale. What I'm showing you here is a simulation of habitable worlds imaging at 100 megaparsecs, where you are not able to measure Cepheid variables with current facilities, but with something like HWO, you can detect and measure Cepheids at 100 megaparsecs. And what that does is that takes you out into the regime where you start getting into the Hubble float. And so you don't need the supernovae or the surface brightness fluctuations anymore. And so you can bypass those entirely. And so keep an eye out this summer for a Habitable Worlds Observatory distance ladder focused science case by some of us. And so I'll wrap up there. I've got a couple summary slides. And so the TRGB is a really efficient way of measuring distances to nearby galaxies. Imaging with Hubble has been revolutionary, I would say, for our understanding of the local volume, its structure, its constituents, its evolutionary history. With over 500 TRGB distances, JWST is going to allow us to get out to 50 megaparsecs, I would say, where there's no shortage of supernovae or especially SBF calibrators for doing things like measuring the Hubble constant. I would say also there's good buy-in by others as well on the TRGB going forward. In cycle 4, there are other substantial programs that will have TRGB components. For example, the J-Virgo program led by Dan Weiss and Abby Lee at Berkeley. It's a 150-hour program to map the Virgo cluster, 80 galaxies in the Virgo cluster. It will measure TRGB distances, look at the star formation histories of these galaxies as a function of their environment, provide more TRGB SBF calibrations. There's also a large program by Adam Smersina looking at Milky Way galaxy analogs and looking at their halos to reveal their merger histories and do other sorts of galaxy evolution science. But it'll also be good for measuring the distances as the team has pointed out. And so at the moment, with respect to the Hubble tension, there appears to be excellent agreement between the different distance indicators, as long as you are measuring, or as long as you're comparing galaxy to galaxy distances, and as long as you are not sort of looking at different subsets of the data. And so the Hubble tension appears to be alive and well, with the only hope of escape, I would say, at this moment being an issue with the Type 1a supernovae, or I don't even know. I think that's it. Otherwise, I think the universe is really messing with us. And so I think the TRGB and SBF route can serve as an excellent, I say replacement here. I don't mean we're getting rid of that ladder. I mean as an extra set of comparison for the Cepheids and Type 1a supernovae, in that it will be independent from them. And so at the moment, I don't see a way of relieving the tension, but we're working on it to see if there's another path out. Otherwise, I think the theorists are going to have to deal with it. And then out into the further future, we're going to have TRGB measurements, I would say, in abundance with the Nancy Grace Roman Space Telescope due to launch in 1 to 2 years. And then in about 20 years, I would say, we'll have the Habitable Worlds Observatory, which I think is a true super Hubble, extending the reach of the method even further and perhaps allowing for a 2-step distance ladder instead of a 3-rung distance ladder.